So for today's lecture, we're going to continue where we left off. So I think what we did last lecture was the stress transformations. And then where we stopped, what we ended up with, okay, we have, say, differential element and two positions in our regular XY coordinate systems. And what happens if we now have our coordinate system and then dash system? So this X and this is Y. And this transformation occurs basically by rotating. So this is our regular XY system still, but now we rotate it with respect to an angle of theta. Okay. And then we did an example. I'm going to repeat that example and go a bit more detail to explain a couple more things. The examples on the lecture slides. And the lecture slides I'm recording, so just, there are no lecture slide numbers, so I cannot tell you. But it's basically the first slide of the example. It gives you the description for those online. So in the example, it's as follows. We have a given rectangle. In this case, it doesn't really matter if it's rectangle or square. And we are given sigma x equal to 57.4, sigma y, the y direction, so this x, this y, sigma y in the y direction, that's equal to 75, if I remember correctly, yep, 75. Tau xy is not given, well, it's given is equal to 0 actually. And it gives you the, tells you, okay, well, we can define a rectangle, A, B, and C. And the idea is to find the stresses that act on our segment AB. So if we draw our stresses in the normal direction, that will be our sigma n. And we will have a shear as well. Let's call that just tau n. Let's call that just tau, or tau AB. And the idea is, okay, right, also this angle is given to be 60 degrees. So from the lecture, what we derived was basically a transformation matrix. Let's call that R for now. And we said that's m squared, n squared, 2mn, n squared, m squared, minus 2mn, and then mn, and n here. There's a minus, I will get to that. It was like this. Let's see, where's the minus? Minus on this side. So this was our rotation matrix, where m is the cosine of theta, and n is equal to the sine of theta. So, to be exact. And then we said, well, if we want to have a transformation done, we have our sigma transposed is equal to the transformation matrix multiplied by our regular stresses. So here we see that the stresses basically is vector, is our sigma x, sigma y, and tau xy. That's our stress vector. R is our rotation matrix, function of theta. So we basically plug in theta. And the question is, okay, well, which theta do we need? That was one of the questions we had previously. So there's a reason why I redrew these two figures. So we do in rotation, basically counterclockwise of Yeah, we're doing rotation. Basically, theta, how it's defined here in the rotation matrix, is this rotation angle here between our regular axis and our transformed axis. So if you look at this theta angle and we basically project this one, what can we say about that angle? So again, if you look at this angle here, or this triangle, well, we can say, well, this is a 90 degree. This intersection is 90 degree as well. So basically, theta is equal to 90 minus this new angle here, which we call phi. Okay? So that's our rotation angle. And this angle, if you look at triangle, is the same as this angle here. So in our case, when we plug in our theta here for transformation, we basically have to define this angle here, theta. So now we know theta is equal to 90 minus phi. Phi is given to be 60. So in our case, r of theta equals r of 30 degrees. And once we plug that r in, so once we do this transformation matrix, I'll spare you the numbers. This is not really interesting what the numbers are, but the transformation is of 57.4, 75.00. We get our new rotated coordinates. So this will be equal to 61.8, 70.6, and 7.6. You see, yeah, you can see. So that's our new transformed stresses. So in this case, what are these numbers represent? Well, first of all, this will be your sigma x in your transpose system, your sigma y in your transpose, and your tau xy in your transpose system. So in this case, sigma n equals 61.8 and tau ab equals 7.6. And if you would basically draw another axis, so if you would be looking at this sigma y transpose, that will be your second one, which is 70.6. Okay. So that was the small example. I think this is example 1.1 in the book, at least if you have the 6th edition. And with that said, that was the example we did. And we're gonna, let's see, get rid of this one. No. So the next question is that we can answer actually is, so now we know that basically stresses will differ in value based on the rotation angle of our segment compared to our, say, zero angle. Then the question arises, okay, well, what happens to the stresses when I rotate? Let's say from 0 to 90 degrees. And the question is, okay, will there be a maximum? So that's an important question. So can I find a rotation angle and where we basically get a maximum stresses or minimum stresses? And if I rotate enough, will I find something that basically gets rid of one of the stresses, if not? So to do that, basically pick up one of the stresses. We redefine our stress x in the dash coordinate system. So basically we multiply m squared plus sigma x, m squared sigma x plus sigma y n squared plus 2 times mn multiplied by tau xy. So what we get is, we just rewrite this out. Let's do this here. Our dash system, sigma x, sigma y. So we just look at our sigma x and dash for now. Okay. So in that case, we have sigma x cosine squared theta plus sigma y sine squared theta plus 2 times tau xy cosine theta. So that's the what we have. So just like any other function, we can say, well, this is basically, what this basically says is that sigma x rotated is a function of our theta, and of course the fully exact function of our stresses. So like any other function, if we want to find a maximum or minimum, we take the derivative, we set it equal to 0, and we can say something about it. So basically, if you have a function of x, so we take this df x dx set it equal to 0, and this gives us a global mean stress max. Gives us a minimum maximum. And basically that's what we do here as well. So if you do that, so yeah, I did not write that out. Yeah. Theta, we do that. And the next step is, of course, once you solve it, we set equal to 0, and we solve for theta, basically when it's maximized or minimized. And if we do that, what we get is tan to theta is 2 tau xy 9 over sigma y sigma x. I really don't want to do the derivative. So that's what we get. So let's write that here. So what we get is, by taking our setting this equal to 0, we can get tan to theta is equal to minus 2 tau xy sigma x minus sigma y. And then if we, of course, if you want to just have a theta out of it, you can rewrite this as bit. So we take the inverse of tan and then divide by 2, so we get 1/2 tan minus 1. So that's the inverse. And then of course it is xy sigma x and sigma y. And there's another solution. We have this angle, and of course, if you look basically at angles, say you have a sine, you have the zeros, and basically repeating. So in this case, when there's the zeros repeating is when you have 1/2 tan minus 2xy minus theta plus pi over 2, which is 90 degrees. So these are our two solutions, where basically when we have p theta, p sigma theta, p theta equal to 0. And these two axes, basically that it's basically the same as defining one axis and then saying 90 degrees off a particular axis. So it's nothing else than that. These two axes are very important because we also call these principal axes. And if you plug this in, if I plug this axis, our thetas into our equation here and get our transformed axis system, our transformed stresses, what we'll notice is that actually there are shear stresses disappear. So we only have two stresses acting on those planes. Those are our sigma 1 and sigma 2, which are representing the transformed sigma x, sigma y, which are, like I said before, our principal stresses. They act on our principal axis, and these are known as our principal stresses. And that might be very useful to us, so we can basically come up with a rotation, we can angle, we can determine to coordinate our, say, product in such a way that we don't have to deal with any shear stresses. And of course, we can basically also derive whether basically for these two stresses, what the equation actually looks like by plugging in our thetas and deriving it a new expression on basically based on sigma x, sigma y's of that. And if we do that, what we get is that our principal stresses equal our normal stresses in x and y over 2 plus half square root sign sigma x and sigma y squared plus 4 pi x y squared. And then sigma 2 will be at 90 degrees, so basically it changes. So this will be our equation if we would derive it for the maximum principal stresses. And we can repeat the same exercise basically by looking at, instead of looking when say sigma x is equal to 0, but say sigma tau xy equal to 0, and we can repeat the same thing, we find a new angle, and based on that we can define new stresses, and we can see that the maximum shear stress or minimum occurs at so either plus or minus, depending on your maximum min or sigma x minus sigma y squared plus 4x pi. Okay. So that's where our maximum stresses occur. And that is the same as saying sigma 1 plus sigma 2 over 2. No, this should be minus, sorry. So that gives us our three principal stresses. So we can actually change the angle in such a way that we basically get rid of our shear stresses, or we can actually maximize it at a location. And what we also notice is basically we have three angles, tau x, sigma 1, sigma 2. And once we know these two angles, we can also defer that at 45 of those angles. So if we have, say, two new angles, sigma 2, let's call this. Well, our new axis is defined, sigma 1. There are maximum curves at 45 degrees. That's what our tau is max / min. That's also something that you can get out of this. So we did basically we completed stress transformation matrices, and we can move forward. And before we move forward, we're gonna do one more thing about stress transformation. It's looking at basically with the concept of Mohr circle. And Mohr circle is basically a visual representation of our principal axis. And it can be very useful just to determine, go to a slide. So this will be for those online, slide 60, I think. 59. So it's basically a visual representation of our axis system and our so let's see how we can use that to our advantage in some cases. So for Mohr circle, we basically assume a couple of things. We start again with our normal stresses and our normal axis. That's sigma x, sigma y, tau xy. And we basically draw a couple of things. We have a couple of different givens that we can utilize. First is that the center of the circle is at sigma x plus sigma y over 2. Comma 0. That's our x and y coordinate system. So if we have our axis, and this axis we will have our stresses, direct stresses, and on this axis we have our shear stresses. And notice that positive is defined downwards positive, not like the figure says upwards positive. And we also know that the radius of the circle, r, is basically defined by our, say, principal stresses. Similar to our principal stresses, actually. Sigma y squared plus 4 tau xy squared. So those are the two conditions that we can use. And using that, we can basically, if we have our tau sigma x, sigma y, and tau xy, we can construct a Mohr circle, and based on that, we can easily determine what our stresses are and how they basically rotate. So if we would have an estimate sigma x, sigma y, we would draw our circle. We have our center, C, and it goes to point R. So yeah. We have our circle with radii, center C, and of course radius R. And we can determine that. And then we can use these two functions to basically determine our circle, or we can just use coordinates. And if we want to do coordinates, what we can do is we can draw a couple of points on it. That's basically sigma x comma minus tau xy and sigma y comma tau xy. So those will be two coordinate systems on our circle. So let's call that Q1, and then we have Q2. So that's one other way of basically constructing a circle. Instead of using the radius, you can just find C, Q, Q1, Q2, and then you can still try your circle because based on C and Q, C radii. Yes?
So you told us that it's the sigma x minus tau x y and then y tau x y. But
yeah.
How do you find out on the circle which one is the x, y, and which one is the, because the axis just says it's just the stress times plotted against the shear stress.
So by
how do you find the x and y on the Mohr circle?
Oh, this one, like if it's not let me see. It doesn't really matter because instead of these 2 points, you would get these 2 points if you plug it in. It will still lay on the circle. As long as it's basically opposite. So for one, you use sigma x, sigma y, and then you do tau x minus tau x and plus tau x y. You could literally say sigma y minus tau x y, comma sigma x, comma tau x y. You still get the same principle out of it. It's just convention to use these two, just like it's convention to draw it negative downwards. I don't even remember why it was negative downwards, but it's convention. And the benefit from this is basically, if you want once you have your radius and once you've constructed your Mohr circle, you can basically visualize certain points on it. Because if you draw it a bit better, what we also know is that, say, let me say this correctly. Because once we have this angle, let me see, why is this? I think this basically becomes 180, of course, because it's a straight angle. Then I think this angle is defined as 2 theta. So once you have a theta, you can construct, basically rotate it visually to come up with a different point. Say if you know, say at a given angle, say theta x, you can rotate that with respect to this axis 2 theta out. Say, sorry. So if you've given theta, you can basically rotate out with 2 theta, and you get your new coordinate system. So if you've given theta, you can rotate it by basically 2 theta. Sorry, this angle is 2 theta. So if you constructed your first points x and y and z, so any rotation from this, say normal normal coordinate system or untransformed coordinate system, if we rotate by any theta angle, we can rotate on our graph by 2 theta, and we get our new tau and our new sigma out of it. So it's basically, in this case, gives us sigma n and sigma n out of it. And then basically the 180 degree from this one gives our sigma y. So it's basically a visual representation how you can now use, instead of just using transformation coordinates, calculation wise, you can construct the circle, and then you can visualize how it rotates, and that basically represents rotation of our coordinate system. And then we can rotate it even more, have theta, and then probably even more, etc. Comes some visual representation of our transformation matrix. This was useful back in the day when calculations were just not ready to be available. Nowadays, Moore circle is still being used as a visualization tool, but not as frequent. And definitely in calculations, since everything is now programmed, these things become more or less obsolete. The principles, however, of it are still fundamentally true and fundamentally valid, because this basically gives us the basis of fatigue, crack propagations, and a lot of other stuff that we can only use. So it's still based on these principles, especially when we go to tin plates, we use of assumptions that basically this is the fundamental. And of course, what we discussed was stresses, sigma x, sigma y, sigma z, sigma x, sigma y, and tau xy. The same can be, of course, also done for strain coordinate systems. So we can go from sigma x to our new coordinate system, sigma x dash of tau epsilon x to epsilon dash x. And those things I will just give you for sigma epsilon x, but you can do the same thing. You can start out with the same principles. You can write the equations. You can come up with a transformation matrix. And in this case, it will be equal to epsilon y plus epsilon x over 2 plus epsilon x minus epsilon y over 2 cosine 2 theta plus gamma xy over 2 sine 2 theta. And then if you change these two signs to minuses, then you get epsilon y, and then you can also get gamma gamma xy in the coordinate system. But you can do the same thing. The principles remains the same. You can start off with the equations, do derivations, or just transform the strains, and you just get a slightly different formulation of it. So to recap quickly what we have done so far, we have introduced our equilibrium equations. I'm just going to call it stress, but it's of course valid for strain as well. We've done our stress equilibrium equations. We did our stress transformation. We did our assumptions. So basically we went from 3D to 2D. And now it comes to the question, okay, can we use this to actually solve an actual stress problem? And solving a stress problem, this does not, it includes, but it was not the same as our transformation where we can find, okay, well, this x, y, or sigma x, sigma y, find sigma x dash at theta is equal to whatever. So this is different, what we do here. Here we basically go ahead and try to solve the whole system of come up with a function that represents our stresses, given also boundary conditions that we have to satisfy. And the first thing, and of course, this relies heavily on the fact that we go from a 2D case. So it's a very simplification. Again, the origin of this comes in the 1900s, late 1800s, where we basically had limited resources to solve problems. So we made a lot of assumptions, slim it down, and then we could solve one set of equations or one set of a problem. And to do so, the thing was said, okay, well, even if I have given a problem, I assume that there exists a function, phi, that represents my stress rate, and that's a solution to my stress rate. then the question actually becomes, okay, what's our function phi? So basically you just say, I have a function at phi, I don't know it yet, but I will come up, based on the boundary conditions, based on the stress that I've given, I will come up with a function that basically satisfies the boundary conditions, and that will be my solution. So with that said, we said basically then the first one to do this was Ares, hence the name Ares stress function. And he said the following. Well, I said, okay, I have a function phi, and I say that my sigma x is defined by the second derivative of my function phi with respect to y. And my sigma y is equal to my function, but then the second derivative with respect to x. And my tau xy is given as the negative of my derivative, the function, which respects both x and y. We basically started with this. He said this, I need to find a function that if I differentiate it twice with y, I get my stress as an x. If I differentiate twice with x, I get my stress in y. If I differentiate it with x and y and take the negative of it, I get my tau xy. And to do so, he did start with this, basically with our 2D stresses. And if we remember our 2D stress equations, we had sigma x, delta x, partial x, plus tau xy, partial y, no body forces, so x is 0, it's equal to 0, and we have partial tau xy, partial x, plus sigma y, partial y, is equal to 0. Yep. Those were our two basically equilibrium equations that we start off with. And then we had also, if you remember correctly, in the 3D case, we basically had a set of equations, and we had basically 6 compatibility equations. So those 6 compatibility equations actually reduces to one compatibility equation, and they reduce to, let me actually write it down here. I'll write all of it down. I know it's a bit much, but it's good to know where it came from. And then we add a couple of other ones. We add 2. So these are 6 compatibility equations. If you go for stresses, we basically set variation of our stresses in Z are equal to 0. It basically reduces to one compatibility equation that is left over, and that will be basically this one. So So basically, variation of anything in Z goes to 0. So any derivative with respect to Z disappears. So that means here we have a derivative with respect to Z, but there's no variation with respect to Z, so that's equal to 0. So basically, this is derivation with Z. So this disappears, there's a function of Z for derivative y squared by this strain in Z. Well, this one by definition, if this is equal to 0, this must be equal to 0. So I've got variation with Z. This basically it's 0, so this must be equal to 0. Variation with Z. So variation with Z. This has stresses in Z, so this is 0. This is stresses in Z, so this is 0. So this is valid. Again, variation with Z here. So this is 0. This is stress in Z direction 0. Stress in Z direction 0. By default, this must be 0. And by the way, I think this is a Z anyways. So this also variation with Z. So this one drops out as well. And then we have here variation with Z. So this is 0. Therefore this is all 0. And therefore this must be equal to 0 as well. So epsilon Z must be equal to 0. At least the second derivative with x and y must be equal to 0. So the only thing that is not a function of Z is this one. And we can, now what we do is basically use our Hooke's law. Basically says epsilon x is equal to 1 over e sigma x minus mu sigma y. Epsilon y is equal to 1 over e sigma y minus mu sigma x, and gamma xy is equal to 1 plus nu over e tau xy. We can plug these into this equation, and what we can do is we can rewrite this equation in terms of the stresses, and what we will get is, and I will save you. So this derivation stresses, by the way, is in the lecture sheets. But due to time issues, I want to finish this chapter of stresses this lecture. So what we get is the following compatibility equation. So we have 3 important equations. These are our equilibrium equation. And this is our compatibility equation. So these are the 3 stresses. Basically, for our function phi, it must satisfy our stress equations, equilibrium, and must satisfy our compatibility equation. And this compatibility equation came from the fact that we have a stress displacement field of 3 coordinates and 6 equations. So in order to have basically displacement field that satisfies all the equations. We needed some compatibility between those relationships. So if we now take this into account and we check it with respect to our compatibility equations. So we know, we said our area stress function phi must give us these stresses. And now let's plug in these conditions into our stress equations and let's see what happens. So we substitute for 1, substitute our phi into our stress equilibrium equations. Okay, so 1 and 2 give us the following. So we have variation with sigma x with x. Sigma x is defined as this. So we get a variation of sigma x with x, we get this. Yeah. And then we have a variation of tau xy with y. We know our variation with tau xy, so we get a minus here, because plus minus here. Let's just say y, and we get 5 with x with y. And then, of course, this is, you can just take it. Take the differentiate with x out of it and put a y in the bracket. So this is equal to 0. So our first equilibrium stress equation is satisfied. And we can repeat that for our second equation as well. So repeating this, this was our first equation, our second equation. Negative plus sigma y, so that's this one. And this one is also satisfied. So if when I started with, I said, okay, I have a function of phi that must satisfy this equations or this form, and if I plug it back into my stress equilibrium equations, I know regardless which function I choose, as long as it satisfies these conditions, I've already automatically satisfied my stress equilibrium equations. And of course, a solution is only valid if we can also satisfy our compatibility equation. So we cannot have a solution of phi that has such form that our compatibility is not satisfied, even though sigma our two stress equations are satisfied. So for the third one, we do the same trick. We basically plug it in, do the take it out of the brackets. What we get is our compatibility equation say sigma x squared plus sigma delta x differentiate with x and y, and then we can plug in sigma x and y. This must be equal to 0. So what we can do is just take it out. So we get, it's just quadratic equation. So we get the power of 4x plus 2 power of 4x squared y squared plus 4 derivative of 5 y is equal to 0. And this is 4, again 4. Yeah. And this equation, normally we say it's a compatibility equation, there's a special name to it, and this is known as the biharmonic equation. So now what I can do is, I can look at my problem, I can define a function that satisfies these three conditions. Yeah, based on my function definition, I get my stresses sigma x, sigma y, and tau xy. And I check it with my stress equations and my compatibility equation. This satisfies. It basically gives me a correct solution. Now the question is, how do I define my function phi? Can I define anything? Not exactly, because at the same time, these conditions must be satisfied, but also the boundary conditions. Must be satisfied. And what we'll see is that boundary conditions actually determine how sigma x, sigma y, sigma tau xy will look like. So we have these three equations that satisfy our stress function. So what we said is, let's define a function phi that has the following functions. Sigma x is phi squared y squared. Sigma y is phi squared x, and then tau xy is the negative of phi squared delta x delta y, or partial x partial y. And by the way, you can write this slightly differently as the non-operator. You can use that as well. So as long as we have our biharmonic, if we manage to satisfy our biharmonic equations, then the solution will basically be a valid solution. So let's look at an example and use that. So now what we do is we assume a given function. So we have a problem. We can do it two ways. We can define a function phi, and we can see what basically the boundary conditions are. So let's define phi. In this case, we define phi as a very simple equation. We say it's x squared plus by squared, byx plus c squared. Now I can look, if I have such a function, which boundary conditions I can satisfy. So if you now look at our equations, now our sigma x is defined as second derivative with respect to y. So second derivative with respect to y, that's c, 2c. Sigma y, second derivative with respect to x, that's only a, so 2a. Tau xy, second derivative with respect to x and y, so these two drop, and negative sign, so it's negative b. So those are my stresses. Do those stresses satisfy the biharmonic equation? So I take the fourth order derivative with respect to x. It's no fourth order derivative, so that's basically 0. Plus 2 times second derivative with respect to x squared y squared. So there are no second order derivatives with respect to x, y squared, so there's basically no x squared, y squared terms in it, so that's 0. And then no fourth power order, so there's also no y to the power 4 squared, so that's 0. So by my biharmonic equation is also satisfied. So now I know that this equation, I basically say, okay, what kind of boundary condition does it satisfy? Will satisfy a boundary condition similar to the following. So we have a constant stress in x. So sigma x will be equal to 2a, or sigma y be equal to 2. Oh, no. So sigma y is equal to 2a. Sigma x is equal to 2c. And then I have also shear stress in tau xy, which is minus b. And of course here, minus b. And I have 2c and 2a. So that's one way of solving this problem. Basically, you start off with any function, and this could have been any function that I could assumed. I could have added 5 more terms to it, which that means is that basically, as long as I satisfy my biharmonic equations, the stresses that this function can solve are defined as whatever my terms are. So if I add here another d in it, say with respect to y, x, and another minus something else in it with respect to y, x, e, as long that I will get basically here minus d plus e, and probably I was still satisfied, but then my here my shear stress is defined by basically b, d, and e. So that's one way to solve it. Another way to solve it is, this is a very simple problem, of course. Is if we go a bit more complex, is we'll basically have given our given a function like f phi, and given a set of boundary conditions, and now we have also actually determined the coefficients of a, b, c, and d, and e. So let's assume in this case r phi is equal to 2a. Sorry, it's equal to a squared, ax squared plus b x squared y plus c y to the power 3 plus d of 5x squared y to the power 3 minus y to the power 5. So now what we have to do is determine a, b, c, and d coefficients. Given that, we're basically given a problem with a set of boundary conditions. So this one's clamped. Let me go to the lecture slides. It's too small, I cannot read it. Okay, so we have given, this is, I think, one of the last lecture slides. Yeah. So this is H and H, so 2H in total, and we have a distributed load equaling to Q, which is any given distributed load. And I would basically have to solve for not only A, B, C, and D, but we have to solve it in such a manner that satisfies these boundary conditions. And these boundary conditions are actually needed in order to get a solution for A, B, C, and D. But let's start again by defining our stresses and sigma x, sigma y, and tau xy. So sigma x, phi, that's second derivative with phi, with x, with y. and that gives us yeah, 60 minus 30 dx squared y minus 20 d y to the power 3 sigma y divided through 2x is 2a plus by 2by plus 10d power 3, and then minus tau xy. Again, notation wise, phi 2 subscript means the derivative with respect to phi. So the second order derivative. This should be tau xy, sorry. Or phi xy. And that's 2b plus 30 d y squared. And then, of course, our biharmonic equation of must be satisfied as well in order for the solution to be correct. So if you do that, what we get is there are no fourth power of x's, so that's 0 plus 2 times phi xx, y xx. So there are only this term that satisfies this condition. So what we get is 2 times 60 dy, and then y to the power minus 4, or the 4 derivative with phi with y. So that's only one term that satisfies this, so 5 times 4 times 3. And gives us this. And what we see is 160 dy minus 160 dy is equal to 0. So our biharmonic equation is satisfied. So this solution is valid to be used. And now to determine our coefficients a, b, c, and d, we must look at the boundary conditions. So for the boundary conditions, we have a bunch of boundary conditions that we can use. Often is you will probably have more ways to solve this than there will be more than one way to solve it, but we always want to go for the most easiest case. So what we know is that you see, yeah, in this case I have to draw the axis system as well. This is x and this is y. So y is pointing downward positive. So we can tell that here at h plus h and y. Yeah, so the sigma y at y is equal to h. So this location here. At this location, sigma y is equal to 0 based on the boundary conditions. So we know also that y is equal to minus h, that's on this top, right? Then our stresses must be equal to our given distributed stress, so that's minus q. Actually plus q, because y is positive downwards. And then what we also say is on this axis, on this face, so at y is either plus minus h, our shear stress tau xy is equal to 0. So we plug this in, those boundary conditions. So what we get is sigma y is equal to 0 at y is h. So let's look at sigma y. We plug in y is h in there. So we get is 2a plus 2b h plus 10d h to the power 3 is equal to 0. We know that sigma y is equal to q at minus h. So we can plug that in as well. 2a minus 2bh minus 10dh to the power of 3. This is equal to q. And what we have here is at h is y is plus minus h, tau xy. So that's equal to 0 for, so what we get is 2b plus I'm missing y. So it'll be h squared is equal to 0. I want to check again why I'm missing my x. Tau xy.
There should be an x after the b.
I know. So I'm thinking why I'm missing that x here.
And there is one more for sigma x. There should be y after 6c.
This one?
Yeah. So it's cy cubed.
Yeah, you're correct. Let me double check again. Let me see. Minus, that fits in here. There's a minus as well. I'm missing something. Let's see, 2x makes sense. That's 2a. 2b1 makes sense. No x, 10 dy squared, that makes sense. Okay, that makes sense. Sorry, let's get rid of this one for 1 second. I'll get back to this. So from these two equations, we can basically add them together, so these drop. So basically, we know that a is 4a is equal to q, so a is q over 4. So that's our first coefficient that we solve for. Now we can use our tau xy. Wondering, we get 2b plus 30 dh squared is equal to 0. But we have an x here, so I'm wondering what x conditions we have. So this x, I'm looking at this location. So I'm dropping an x somewhere. I'll come back to that one later. X is equal to 0. So another condition that we can look at is basically so if this is our x, so this basically starts at 0x. We have a free edge. So when a free edge, we know that basically no forces and no moments. So our moment at that location must be equal to 0. So now how do we define the moment in around our x coordinate system? That will be taking the integral from minus h or along this surface with respect to sigma x y dy, and then that's what we get is the integral of minus h to h 6c y squared minus 20 t to the power of 4 plus d x is in this case 0, so that's d0 multiplied by d0 multiplied by y squared dy. So what we get is, if we do this integral, we get c minus dh squared is equal to 0. Still don't know how I dropped my x in this equation. Let me see. Could basically evaluate it in tau xy. So this is tau xy. Say it's equal to 0 when we hit this edge. I'm missing something. This one?
Yeah.
So in this case, this is 0, yeah.
Okay.
So it's basically dxy squared, but x is equal to 0, so I just wrote down 0. So basically this
Okay.
drops. So in order to get so if I write this one here, the integral that you have to evaluate is 2cy to the power of 3 minus 4 cy to the power of 5, and you evaluate it at minus h to h, and that gives you c to d h squared is equal to 0. Basically, for some reason, you will basically have, let me see, so we have already a filled in, can determine a, 1, I'm missing the equation. I have to look at this because I'm missing one equation anyways. Do I? No, I actually have enough equations. Because I have now a is given, so I can basically back substitute in these equations. I can use the first equation to write b in terms of d.
Are you missing an x somewhere?
Yeah, I'm missing next year. So basically, I'm just talking this solution procedure right now. I'll do this next lecture in more detail. I have to double check it. So what we do is, once we have a, we can back substitute a into either, say this one. Now it's basically a is not an unknown anymore, it's a known. We can rewrite b as d. And in this case, we could basically back substitute b as d into this one. We can either solve for b or d. And then we can continue in such a way to back substitute d into our the third equation. Basically, we'll at the end of the day we'll have enough the same number of unknowns as our equations.
The negative tau equation, should it not be will be x?
Should be x. Ah, that's my x. Yeah, that's my x. Yeah, because then I can divide x out. Now makes sense. Hey, thank you.
I think we're past time.
Yeah, I know. Okay, we'll continue. I'll recap very quickly next lecture, and then we'll continue with the next topic. Okay, thank you.